Okay, so this is the second part of 8.6, section 8.6, part 2. Now let's actually, so in the previous part we took a complex number in polar form and we raised it to a positive integer. We raised it to a positive whole number exponent. Now what we're going to be doing is, starting with a complex number in polar form, we're going to raise it to a rational exponent. We're going to be taking a root. Okay, so there's this thing called the fundamental theorem of algebra, which says that a polynomial with real coefficients of degree n has n roots or zeros. The only thing is that some happen to be complex numbers. Yeah. So what does that mean? So for example, imagine I have this third degree polynomial, x cubed plus 1. That's a polynomial of degree 3. And it's got real coefficients. All of the numbers are real numbers. And I am looking for its roots, for its zeros. So I set the polynomial equal to 0. And the fundamental theorem of algebra then guarantees that this little polynomial equation, x cubed plus 1 equals 0, should have 3 solutions. There should be 3 solutions to this little cubic equation. I can think, off of my head, I can think of one solution, -1. If x happens to be -1, well then -1 to the third is -1, -1 plus 1 is 0. So -1 is one of the solutions to this equation. But what are the other 2 solutions? We'll answer that at the end of this section. All right, so let's try to find a root of a complex number. Yeah, let's just try to find a root of a complex number. Let me just erase some things here that make no sense. Let's just do it right now by brute force. We'll develop a theorem here in a second, but right now let's just say that this is brute force. All right, so the example goes, this is an example in your notes, but we're gonna do it first by brute force, just kind of by figuring it out on our own. No theorems or anything. So we're supposed to find the square roots, and notice that this is in plural, roots. There's going to be 2. So I need to find the square roots of this complex number, 4i. And I want to express the roots both in polar and rectangular form. All right, so how do I do that? I want to find the square roots of 4i. I guess right now maybe my question is it here? I guess I'm thinking, is it going to be 2i? Is that my answer? Well, 2i times 2i, I think that's going to be -4, which is not quite 4i. So yeah, I mean, I gotta find the square root. So the first thing we should do to find the square roots is express the complex number in polar form. Yeah? So right now 4i is the same thing as 0 plus 4i. 0 plus 4i. And I want to express that in polar form. Alright, so to express it in polar form, I need to find its modulus, its radius. We know how to do that. It's the square root of the a squared plus b squared. So 0 squared plus 4 squared, that's 16. The square root of 16 is 4. And here's, this gets a little bit more kind of interesting here. I gotta find the angle, the argument of this complex number. Well, that's going to be tangent inverse of the imaginary part divided by the real part. Yeah? And remember that the range of tangent inverse is between -π/2 and +π/2. But now 4 over 0, that's undefined. It's undefined. And so then kind of we get into a weird situation here. Where is tangent undefined? Where is for which angles is tangent undefined? And if you remember, tangent is undefined for odd multiples of 90 degrees. So 90, 270, What's 90 times 3? Okay, so 270, 450, so on and so forth. So can you think of an odd multiple of 90 degrees for which, and also think about this complex number, 0 plus 4i. 0 plus 4i. Think about this complex number in the complex plane. If you agree, I mean, if you think, just imagine plotting this point in the complex plane. It's just going to be on the y-axis. It's going to be on the positive imaginary axis. So that angle should correspond to 90 degrees. All right, so this is my complex number in rectangular form. And here's the same complex number in polar form. It's 4 cosine of 90 plus I sine of 90. All right, so that's the first thing I've done so far. I haven't even taken any square roots yet. All I've done is I changed the rectangular form to polar form. All right, so now let me actually try to find the roots. So now what I'm doing is I'm looking for some complex numbers. I don't know what they are, so I'm just going to call them r cosine theta plus I sine theta, such that if you square this complex number, this is the unknown, but if I square this complex number, I should get 4 cosine of 90 plus I sine 90. That's what it means to be a square root. Yeah, so I am looking for some complex number that if I square it, I get 4 cosine 90 plus I sine 90. Then that would say that this complex number is the square root. All right, so let's see. Let me look at this equation right here. How do I square a complex number? Well, in the previous video, we saw that in order to square a complex number, it's just r squared times cosine of you double this angle plus I sine of double this angle. And this should be equal to 4 cosine 90 plus I sine 90, because this is supposed to be the square root. Okay, well then that forces some things upon us. R squared should be equal to 4, which, after we take a square root, says that r is equal to 2. Yeah, there is a plus and a minus when you take a square root, but right now we're dealing, all the moduli of a complex number is always positive. So r is equal to 2. Remember, I'm trying to find the square root of my complex number. Okay, another thing that's forced upon us is that 2 theta is equal or coterminal to 90 degrees. Well, what does that mean? Well, it means that 2 theta is equal to 90 degrees plus 360 times k, so any coterminal angles to 90. And now, what I'm going to do is divide this equation by 2. So if I divide everything by 2, 90 divided by 2 is 45, 360 divided by 2 is 180. And now we kind of have our solutions here. So now look at what happens here. So I have, if k is equal to 0, I'm going to have 2, because that's my radius, 2 cosine of 45 plus I sine of 45, because remember, k is 0, so 180 times 0, that's gone. So cosine 45 plus I sine 45, well, that's 2 times square root of 2 over 2 plus I root 2 over 2, and if you distribute the 2, then that's just square root of 2 plus I square root of 2. Okay, now if k is equal to 1, I have 2 times, and now if k is equal to 1 up here, that would be 45 plus 180. That's 225. Cosine of 225 plus I sine of 225. Okay, and well, cosine of 225 is negative root 2 over 2, and so is sine of 225. And then once I distribute the 2, I end up with negative square root of 2 minus I root 2. Now, if k happens to be equal to 2, then I have 45 plus 360. That's 405. It turns out that 405 is coterminal to 45. And so then I should get the same answer as when k was equal to 0. So when k equals 2, gives me the same answer as k equals 0. Now, if k equals 3, that's cosine of 585, that's going to be 45 plus 540, because it's 180, oops, 180 times 3, that's 540, plus 45, that's 585. And turns out that 585 is coterminal to 225. So if k equals 3, I get the same answer as k equals 1. And if k equals 4, I should get the same answer as k equals 0. And if k equals 5, I get the same answer as k equals 1. So it's really just k equals 0 and k equals 1 that gives me distinct solutions. Everything else after just repeats. So notice that after k1, solutions repeat. So the reason why I have this doodle over here is because these are kind of like the only two answers, really. Yeah, so there were two square roots. So that's it, we have found the square roots. We have found the square roots of our complex number. This is one of them. This is another one right here. That's it. So we started with the complex number 0 plus 4i. The first thing we did was convert it to polar form, and then we just kind of had to guess on what was the square root. That kind of gave us some conditions. We had to think about some coterminal angles, and turns out that there are two square roots of 4i. Just like the fundamental theorem of algebra says, there are two roots. Okay, now let me give you the statement of what's called the Nth Root Theorem. And hopefully that last example sort of motivates this theorem a little bit. So given the complex number r cosine theta plus I sine theta, if you want to find the nth root of that complex number, and remember, to find the nth root is the same thing as raising your complex number to the 1 over n. Just be aware that there's this big connection between nth roots and rational exponents. Yeah, raising something to the 1 over n is the same thing as taking its nth root. Yeah, okay. So if I want to find the nth root of this complex number in polar form, what I'm going to have to do is I am going to take the nth root of the modulus, the radius, and then it's going to be times cosine of the angle plus any coterminal angles to it, divided by n. N is the root that you're taking, plus I sine of the angle plus any coterminal angles divided by n, and k goes from 0 all the way to n minus 1. Yeah? So for instance, up here, what we needed to find was the square root of 4i. We needed to find the square root of 4i. And if you notice here, once we got into playing with this variable k just went from 0 to 1. So over here, that's why k goes from 0 to n minus 1. It's one less than the root that you're taking. This makes taking roots of complex numbers a little bit quicker, a little bit more procedural, rather than having to do brute force. So this is a nice little theorem. So let's put it to use. So right now what I want to do is I want to find the fourth roots of -8 plus 8 root 3i. And I want to write the roots in polar and rectangular form. Alright, so give yourself the challenge, pause the video, see if you can find, you should end up with 4 fourth roots. You should end up with 4 distinct fourth roots. Alright, so let's see, let's go through the procedure. The first thing I'm going to do the first thing I'm going to do is I am going to change the problem, to, or rather the complex number to polar form. Alright, so let me rewrite it in polar form. Okay, so then that means I gotta find my radius. So that's going to be -8 squared plus 8√3 squared. Okay, well that's 64 plus 192, because that's going to, if you square 8√3 raise that to the second power, that becomes 64 times 3, and 64 times 3 is 192. So 64 plus 192 turns out that that is the square root of 256. Oh yeah, and that's nice because that's just 16 right there. Okay. So I know that my radius is 16. Now let me figure out theta. Alright, so tangent inverse of b over a. Alright, so that becomes tangent inverse of negative square root of 3. Now, what's tangent inverse of negative square root of 3? So you're looking for an angle in quadrant 1 or in quadrant 4 for which tangent is -√3. I think that's going to happen in quadrant 4. That's going to happen in quadrant 4. If you were to just punch this into your calculator though, this would say that this is -60. But then you got to think about its coterminal angle, because we want our arguments, we want our theta. Anytime that we're dealing with a polar form of a complex number, we want the theta to be between 0 and 360. So this is going to become 300. These guys are coterminal. Alright, so then the polar form goes something along the lines of this. 16 cosine of 300 plus I sine of 300. Yeah? Okay, so we've done that. So we haven't even taken any roots yet. We haven't taken any roots. Now the problem asks us to find the fourth roots of this value. So I want to find the fourth root of my complex number. So the fourth root of 16 cosine 300 plus I sine 300. That's the same thing as saying 16 to the, well, cosine 300 plus I sine 300 raised to the 1/4. Okay, at this point I gotta kind of look at DeMoivre8's theorem a little bit. Let me go look up here. Alright, so it says that it's going to be the nth root of my radius times cosine of, right now my angle theta is 300, so 300 plus 360k divided by 4. This is a 4 right now because we're taking fourth roots in our example. Yeah, and k is going to go from 0 all the way to 4 minus 1, so 0 through 3. So let's see, let's employ DeMoivre8's theorem right now. So fourth root of 16 times cosine of 300 plus 360k over 4 plus I sine of 300 plus 360k over 4. And remember that k goes from 0, 1, 2 to 3. And so for each value of k, I'm going to get a different root. I'm going to have 1, 2, 3, 4 of them. Let me just clean this up a little bit. What's the fourth root of 16? Well, the fourth root of 16 is just 2. So this becomes 2. And then what's, this is going to become cosine of, what's 300 divided by 4? 300 divided by 4 becomes 75. And 360 divided by 4 becomes 90. So 75, 90. And k still varies between 0, 1, 2, and 3. Alright, so technically here we're done, but now let's actually differentiate each single root. So for instance, if k is equal to 0, I have 2 times cosine 75 plus I sine 75. That's the polar root. But now if I change this to rectangular form, I'm going to use my calculator here because I need to figure out what is cosine of 75. This should be 0.52 plus 1.93 I. So what I did here is I said 2 cosine 75, 2 times cosine of 75, that's 0.52, and 2 times sine of 75, 2 times sine of 75 is 1.93. And you should verify this. Right now, make sure your calculator is in degree mode. So now if k is equal to 1, what do I have? If k is equal to 1, I'm going to have 2 cosine of, well, 75 plus 90. That's going to be 165. Plus I sine of 165. Okay. And if I punch this into my calculator, I get the following. Negative 1.93 plus 0.52 I. Now, if k is equal to 2, I'm going to end up with 2 cosine of, if k is equal to 2, that would be 180 plus 75. 180 plus 75 is 255. Okay, and if I punch this into my calculator, this becomes negative 0.52 minus 1.93 I. Lastly, if k is equal to 3, I have 2 cosine of, it's going to be 75 plus 270. 75 plus 270, that's 345, plus I sine of 345. And my calculator tells me that this becomes 1.93 minus 0.52 I. And those are my 4 fourth roots right there. So Hopefully we agree on the process and on the answers. All right, so next example. You're supposed to find all solutions to this equation right here. So again, pause the video, give yourself the opportunity to try this problem. See if you can handle it on your own. All right, let's see, how are we going to answer this? So let me first begin by trying to solve this, the equation that I was given. So x to the fifth plus I equals 0. Well, that means x to the fifth equals negative I. And let me rewrite this so that it looks more like a complex number. So 0 minus I guess I'm going to say. So this the real part is 0, the imaginary part is negative 1. And I guess x then is going to be equal to the fifth root of 0 minus I. Yeah? Now, the fundamental theorem of algebra guarantees that there should be 5. There should be 5 fifth roots of this complex number. Okay. So let's find them. What do you suppose the first thing to do here is? What I would do first is change 0 minus I to polar form. Yeah? Okay, well, that means we gotta figure out what is R. That is the weirdest R. Oops. So R is going to be 0 squared plus negative 1 squared. And well, that's square root of 1, so 1. That's R. Now theta. Theta is going to be tangent inverse of the imaginary part, negative 1, over the real part. This is going to get weird. So now you got to think, tangent inverse of something undefined. When is tangent inverse undefined? Again, we said that tangent inverse is undefined at odd multiples of 90 degrees. So 90 to 70, 540. Sorry, yeah, 450, not 540. So also think about this complex number, 0 minus I. So think about this little complex number here. I'm gonna kind of illustrate down here. Think about how it looks like in the complex plane. In the complex plane, so these are my reals, this is my imaginary axis, and 0 minus I, well, 0 minus I is down here. That's 0. That's 0 minus I. So what's that angle? What is this angle? What is the angle made here? I would say that that's 270 degrees. Yeah, so 270 degrees. That's why tangent is undefined, because tangent of 270 degrees it's undefined. It's a vertical asymptote. All right, so I think I have what I wanted. I have the polar form of my complex number. So I have the following. So remember, right now I needed to find the fifth root of 0 minus I. Well, that's the same thing as the fifth root of 1 times cosine of 270 plus I sine of 270. Yeah? Now this is where I gotta use DeMoivre8's theorem. DeMoivre8's theorem, and let me give myself more room here. Here, this is how I conclude this is DeMoivre is that this should be the fifth root of my radius. That's not going to be too difficult to compute, times, and then it's going to become cosine of 270 plus 360k over, since I'm taking a fifth root, then this is 5 down here, plus I sine of 270 okay, and k goes from 0, 1, 2, 3, all the way to 4. Okay, let me clean this up a little bit. Well, this becomes 1, and then this becomes cosine of 270 divided by 5. 270 divided by 5 is 54. And 360 divided by 5 is 72. And again, k varies all the way from 0 to 4. Alright, so we're kind of almost there. Now we just gotta play with this counter 0, 1, 2, 3, 4. So if k is equal to 0, what's going to end up happening is we're going to get the following. I'm going to get cosine of 45 plus I sine of, sorry, not 45, 54 and yeah, there is an equivalent polar. There's whatever rectangular form over here. Let's see. Cosine 54 is, I'm going to round to the nearest tenth, so it's 0.59. And sine of 54 is 0.8. Something like that. Yeah, I don't care for the rectangular form right now. I just need to find the roots, and I'll leave them in polar form. If k is equal to 1, then I have 54 plus 72, and that's 126. So cosine 126 plus I sine 126. Whatever the rectangular form is, you can figure it out using your calculator. If k is equal to 2, we end up with cosine of 198 plus I sine of 198. If k is equal to 3, I should end up with cosine of 270 plus I sine of 270. And that's not too bad. I know that cosine of 270 is 0 and sine of 270 is -1, so 0 minus I. If k is equal to 4, I have cosine of 342 plus I sine of 342, which whatever, it has a corresponding rectangular form. So those are my 5 roots. Those are the 5 roots that I'm looking for. Yeah. So I was looking for, remember our goal was to find the 5th root of 0 minus I. Yeah. The first thing we did was change the 0 minus I to polar form. And then once we had it in polar form, we used DeMoivre's root theorem. And we found the 5 roots. There are 5 fifth roots. Yeah. Okay. So hopefully you were able to follow this procedure and you agree with the answers. Last example. Let's find all of the solutions to this equation right here, x cubed plus 1. So according to the fundamental theorem of algebra, I should be able to find 3 solutions to this equation. Yeah? So let's see. I have x cubed plus 1 equals 0. I'm going to try to solve for x. So then that says that x cubed is equal to negative 1. And well, right now then that means that x is equal to the cubic root of negative 1. But let me think about it as a complex number. So that's the cubic root of negative 1 plus 0i. Yeah? Okay, and so then what I'm going to do is I am going to try to express the complex number negative 1 plus 0i in polar form. So my r is going to be negative 1 squared plus 0 squared. That's just the square root of 1, so 1. And theta is going to be tangent inverse of 0 over negative 1. Well, that's tangent inverse of 0. What's tangent inverse of 0? What's tangent inverse of 0? And if you were to just punch tangent inverse of 0 into your calculator would say that it's 0, but that's incorrect. That is incorrect in the case of this particular problem. Think about what this problem looks like what this complex number looks like in the complex plane. In the complex plane, this complex number looks like, well, it's negative 1, and there's no imaginary part, so it's right there. That is negative 1, negative 1 plus 0i. That's what it looks like. It's right there. And so then right now what you're thinking is, what's this angle? That's theta. And well, I'm gonna say that my angle should be 180 degrees. Yeah, so be careful. Don't rely just solely on your calculator to find the angle theta. Sometimes you gotta think about the complex number. Envision the complex number in the complex plane, and that might help you figure out the angle. Sometimes tangent inverse gives you directly what you want, but some other times you have to sort of think about it. Okay, so let's see. So we now know how to express our complex number in polar form, and it goes like this. So right now we have to figure out the cubic root of negative 1 plus 0i. Well, that's the same thing as the cubic root of 1 cosine of 180 plus I sine of 180. Okay. Now I have to use the DeMoivre8. Alright, so according to the DeMoivre8 theorem, this is going to be the cubic root of 1 cosine of 180 plus 360k over 3 plus I sine of 180 plus 360k over 3. And my k is going to go from 0, 1, and 2. Yeah? And I'm going to sort of go quickly here. What's going to happen is that this becomes, 1 times cosine of 60 plus 120k, because it's 180 divided by 3 and 360 divided by 3, plus I sine of 60 plus 120. Okay. And the last thing, well, I'm just gonna sort of give you the answers here. If k happens to be equal to 0, I'm gonna give you the rectangular form of the answers. The cubic roots are going to be 1/2 plus square root of 3 over 2i. If k happens to be equal to 1, I'm going to end up with just -1. And if k happens to be equal to 2, you should end up with 1/2 minus square root of 3 over 2i. You should verify this. Actually go through the cosine of 60, that's if k is equal to 0, sine of 60, that's what you should get. And those are my 3 roots. Those are the 3 solutions to this polynomial equation. So this polynomial equation, x cubed plus 1 equals 0, has 3 solutions. -1, and this complex conjugate pair of solutions. Okay, well, that's it for this section. Thank you, and I'll see you in the next video.